Hello everyone, this is Altamash from Paanduv Applications Private Limited, and today in this video I'm going to explain you the laser optimization technique. In LPBF, many defects persist even after optimizing laser power or scan speed. The root cause often lies in the how laser energy is distributed, not how the energy is used. In this video, I'm going to explain how laser beam shaping analyzed through AM PravaH helps control melt pool stability and thermal accumulation in multi-layer builds and the surface finish. We analyze a ring laser beam shaping simulation for a multi-layer LPBF build using AM PravaH. The case study consists of 5 layers and 3 tracks scan strategy, allowing us to observe melt pool behavior, thermal evolution, and defect tendencies under a shaped beam profile for titanium-based alloys. So, laser beam shaping controls how energy is spatially distributed on the powder bed. Unlike a Gaussian beam, which concentrates the energy at the center, a ring beam redistributes this energy outwards, reducing peak intensity, and steep thermal gradients. This results in a more stable melt pool, reducing recoil pressure and improves heat distribution between the molten zone and the heat affected zone. Here we can see the laser movement across your 5 layers and 3 tracks. This scanning approach is critical because because of your inter-track and inter-layer heat interactions strongly influences your melt pool stability. AM PravaH captures all these transient effects, enabling realistic evaluation of industrial LPBF conditions rather than isolated single track studies. So by using virtual probes or thermocouples, AM PravaH monitors your thermal evolution across second and the third track. This allows precise tracking of thermal overlaps between the layers and identify the regions of which are prone to your overheating or insufficient melting. Such an insight is really helpful when you are optimizing your scan pattern strategies as well as essential for repeated part quality. So in this slide, we shows that the thermal profile of your fluid, which is your melt pool, across successive layers. Uh, as each new layer is processing before the previous one fully cools, thermal accumulation occurs. AM PravaH enables scalable additive manufacturing simulation through efficient domain decomposition, and this happens by dividing your large volumes into parallel subdomains for high performance computing. This allows accurate as well as full scale modeling of your thermal history, melt pool dynamics, and your layer wise heat accumulation, making production scale LPBF simulations computationally feasible. AM PravaH enables detailed build defect analysis, including lack of fusion, porosity, and density variation. By correlating your thermal profile with your defect formation, we can clearly distinguish high temperature and low temperature regions. This helps identify whether the defect is originated from an inefficient energy input, excessive heat loss, or unstable melt pool behavior. And in LPBF, we have your thermal accumulation fundamentally alters your melt pool dynamics, cooling rate, and residual stress and microstructure as your height increases. AM PravaH combines high fidelity multi physics simulation with custom laser beam shape modeling, enabling systematic and as well as very efficient evaluation of beam profiles like your ring beams. This shift your LPBF process development from your trial and error parameter tuning towards a deliberate energy redistribution engineering, especially important for high power production scale systems. So, if you're working on LPBF or your laser beam shaping, we would value your perspective, what challenges you are facing with your problem. Comment down below. Our team is going to reply to your question as soon as possible. Thank you so much.